this is just an application of different functional form, the double log linear double log model, as well as semi-log model, the one we discussed or explained last week. The first question explains when each of the following model is appropriate to be used. So it depends on how we want to interpret the estimated coefficient, the estimated slope coefficient. You want to estimate as electricity, then use double log model, and you want to estimate growth rate, and then you can use log linear, and you also can use what we call the linear log model for other model. So as given here for double log model, if scattergram of log y and log x shows a linear relationship, then this model is appropriate. In practice, such models are used to estimate the electricity for the slope coefficient, give a direct estimate of the electricity coefficient. Okay, so although we still are able to estimate electricity based on linear model, but if you use double log model, it gives us direct estimate. We do not need to do any calculation. So model 2, log linear. So log linear meaning that only dependent variable using log transformation, and then independent variable using the ordinal values. So such a model is generally used if the objective of the study is to measure the rate of growth of y with respect to x, and often that the x variable represents time in such model, a time trend. Model 3, this one linear log. Okay, so only dependent variable use log transformation. Okay, dependent variable still use the original values. So this is a linear log or linked log model. So if the objective is to find out the absolute change in y for the relative change for a relative or percentage change in x, then this model is often chosen or used. So given a data set here, CPI as well as money supply. So the following table gives CPI and money supply X for Germany for years 1971 to 1987. So estimate all the 4 different models: linear, double log, log linear, as well as linear log, and then interpret the coefficient of all estimated regression. Then you can just estimate lah. So we have y and x here, linear model, then you just get as usual. So estimate equation just like the normal way. So we have y space x space c space x. That for linear model. Okay, so linear model we get the estimate. So how to interpret? Question and next question 2b, interpret. So interpret the slope coefficient of all estimated regression. So for the case of the first model, linear model, how to interpret? Remember, we can just interpret as usual this one. So as given, this I provide. This is a linear model, so you can interpret as usual. You say that when x increase 1 unit, okay, and then y they give the y decrease or decrease depends on the sign, positive negative, increase or decrease by how much. Okay, you interpret as usual. So for the model 1, the slope coefficient will give the absolute change in the mean value of y per unit change in x. So in terms of we say the 1 billion marks increase in money supply increases consumer price index by 0.2609 unit. So you can just take this estimate and interpret as unit, not percent. Model 2, double log model, so just now 38. Okay. So double log model, you re-estimate, you put log of y. So natural log in use log log is equivalent to ln in Excel. Excel use ln, but in use log. So okay, so you get the estimate. So how to interpret? Remember, this one can be interpreted as percent or elasticities. So you go back to this example. For double log model, we have this model. So the slope beta 1 here represent what we call that absolute change in log of y per 1 unit absolute change in x, which is equivalent. Is the difference between two values of log gives us relative change between the two values. So basically this is equivalent of relative change within y per unit relative change in x. The relative change, you multiply 100, you get percent. But because this one, if you multiply or not multiply, you get the same values lah. Because this one cancel out this one. So whether you multiply or you not multiply, you still get the same value. So you just can take the estimated value and then you can just interpret as percentage, okay, as elasticity or percentage. So for model number 2, the slope give the elasticity coefficient a 1% increase in money supply, increase consumer price index by this one. Okay, number 2. So the elasticity. So 1% increase in the x in money supply increases the dependent variable y, consumer price index, by 0.589%. So you can just take that value and then you can interpret as percent. So 1% changes, 1% change in x, and I mean the y will change, increase or decrease by the estimated value lah. Model 3, log linear. Model 3, log linear. So you re-estimate log y against x only. So now you get the estimate. The estimated slope coefficient 0.002799. So in terms of interpretation, how to interpret? So just recall, for log linear model supposed to be this one, log linear. So we have log y by dependent variable, original values without log. So the slope coefficient represent absolute change in log of y per unit change in x. So this one, it represents absolute change in y per unit change in x, 1 unit change in x. So the absolute change in y in log y is equivalent to relative change in y. This one equivalent to relative change in y. So this one you multiply 100, you get percent change in y per unit change in x. Okay, so percent unit change in y per unit change in x. So for the given example 3, this one, the slope give the rate of growth y per unit in y per unit change in x. So in terms of interpretation, we say that 1 billion marks increase in money supply. So 1 unit change because x is given in billion of marks. So 1 billion marks increase in money supply increases consumer price index by the estimated value 0.0028 times 100. This one you have to multiply 100 because why just now you have to multiply 100 in order to get percent. So previously double log you do not need to, you do not need to multiply, because whether you multiply or not you get the same. Okay, this one cancel out this one, multiply or not doesn't matter. But this one you have to lah. You have to multiply 100 and then you can interpret a percent. So percentage change in Y per 1 unit change in X. This one you have to be careful lah. This one you cannot explain, you cannot interpret as percent. You say that per 1 unit change. For one unit change in X, not 1%, but 1 unit. Okay, so in this case X is measured in 1 billion. So 1 billion marks. Change in will increases, because positive increases the Y multiplied by the estimated value times 100%. Okay. So that's how we interpret. The last one, linear log. Linear log means that dependent variable original values, dependent variable using log. So this one, Y space C space log X. Okay, so you get the estimate. So how to interpret this one? You refer to this one, linear log model. Linear log model. So we have original value of Y, but log transform value of X. So in terms of interpretation, it provides the absolute change in Y per relative change in X, because this one per absolute change in log X. So which is equivalent to relative change in X. Okay, so the difference between the value of log X equal to relative change in X. So this the denominator you have to multiply 100, not not numerator but denominator. So you have the estimated value, your beta 1 estimate of beta 1, you have to divide 100 to multiply. You have to divide this one, you have to divide 100. This one you multiply because above numerator multiply. This one it is actually multiplied. It is multiply 1/100 or divide 100. That's same lah. Yeah, this one. So in terms of interpretation, you say that in this case the slope give for model 4 linear log. The slope give the absolute change in Y for a percentage change in X. But you have to divide by 100 first. So 1% increase in money supply. Okay, this one per unit. This one 1% change, 1% change, and then unit in Y. Y in unit. Okay, X in percent. So 1% increase in money supply increases consumer price index by the estimated value 54 something divided by 100 unit. Yeah. So this one you say unit and this one percent. The percent is the X 1% increase in X. So you have to be careful. This one, which one should be interpreted as in unit, in the or in percent. So this one divided by 100, but X in percent, Y in unit. Because Y original value, X the one that we use log information. Okay. See, based on the regression result, which model will you choose and why? So it depends. So the choice of the model depends on how you're going to use the model, how you're going to interpret. If you want to interpret as elasticity, then use model, double log model. Okay. But if you want to make comparison, which one is the best in fitting the data, then remember you can only compare R square for the model that use the same values of dependent variable. Okay, so you keep in mind that comparing R square values of the various model, the dependent variable must be in the same form. So for example, this one, you can only compare R square model 1 and model 4 because they have the same original value of y. Similarly, you can compare R square model 2 and 3 because they have dependent variables are the same log of y. But you cannot compare model 1 and model 2 because the model 1 and 2 have different y and log of y, although originally y, but this one log of y, so no longer the same form, in the same form. So you should not compare R square when dependent variables are different. Okay, you can only compare if the values of dependent variables are exactly the same, then you can compare the R square, and in order to say which one is better in explaining the variation in the dependent variable. That's section 4. So here we have, section 4, we have 6 questions, but only the last 2 we have data for practical example. So question number 1, I already explained in lecture before break. So the difference between perfect, coordinality, and imperfect. So try to explain this term without looking at now, perfect multiplicity and multi-coordinality. So perfect coordinality happen when 2 or more independent variables have a perfect linear relationship, while in case of multi-coordinality exists when 2 or more independent variables are highly coordinated. Number 2, explain why multi-coordinality is a problem for the square estimation. So as explained earlier, multi-coordinality exists when 2 or independent variables are highly correlated. Each slope estimate in and on a least square regression give the average change in y for a one unit change in x, holding other independent variable constant or remain unchanged or remain the same, what we call as paribus. When one independent variable is highly correlated with another variable, then when one variable changes value, so does the other. So in such a situation, meaning that the normal interpretation is no longer the same, no longer correct. So normally when we interpret parameter as a parameter, we say that represent the estimate of change in y per one unit change in x by holding other x to be unchanged or remain the same value. But when we have linear dependence between x, then we no longer able to make that interpretation, because when x change the value, the related x will change the value as well. When x, let's say x is linearly correlated with x1 and x2 are linearly correlated. When x1 increase 1 unit, x2 will increase the value as well, so they are related. Okay. So when one independent variable is highly correlated with another, then when one variable changes its value, so does the other. In such situation, it is difficult for the least square procedure to estimate a slope for either independent variable. The slope coefficient of the multi-coordinate variable will have larger standard error than if there were not any multi-coordinate. Number 3, rank the following models, listing the model most likely to have or to suffer a multi-coordinate problem. So we have 3 different models. So identify which model most likely to have a problem, which one has less likely, and which one comes number 3. So the first model, we have dependent variable, consumption, independent, wealth and income. just like our previous example lah. So there is possibility that we have the problems of. So this one is not perfect. Okay, most likely it is imperfect if there is problem of multiplicity, because wealth and income normally related, but not necessarily, but normally. Okay, normally those have better income have better wealth. Okay, normally, but not necessarily. So there is a possibility of having multiplicity for model A. So for the possibility of having multiplicity, we just need to look at the independent variables, because the problem happens when there is linear independence between independent variables. Number 2, the next model, dependent variable revenue from product sales. The independent variable, we have numbers of buns used, the number of product used, and price. So x1 number of buns used, x2 number of product used, x3 price. So there is possibility. I mean, in this case, normally number of buns used and number of product used exactly the same. Meaning that for one burger, for example, or hot dog, we use 1 bun and we have 1 bun, and inside we have 1 hot dog. So meaning that x1 equal to x2 lah. x1 exactly equal to x2. So we have perfect ordinarity for this case. Okay. For model B. Model C, dependent variable. So price not really a problem lah. So price and the numbers. Okay, it's possible. It is possible, but not perfect lah. Because the more number of buns, and the more the price is going to be higher, the total price. Oh no, this one is the price of bun. Maybe price per 1 unit depends on the definition. If it just the price of 1 hot dog, then should not be a problem. Okay. C, box office receipt per film, independent variable, money spent on advertising, average rating, and then dummy variable. So this one is quite unlikely to have the problems, because it's quite likely to have linear dependence between each of these variables. So money spent, so rating are different things. So money, the rating is not really depending on the advertising expenditure. This is by the film critics. So as and then dummy variable, if the actor has previously won or not. So meaning that for the 3, x1, x2, and x3 is quite unlikely for them to have relationship. So if we sort which one in terms of which one has most likely possibility of having, the problem is B. So B, A, and C. Okay. So you get it here. So 4, when looking at the regression result, what symptom signal multicollinearity? As explained earlier, so you can inspect the result of F statistic, F and the overall significant test and the individual significant test to see whether they are consistent or not. They're supposed to be. I mean, if you only have two variables, then it's supposed to be consistent. Now you have 3, and then you have to check. Another thing that you should look at the significance of the estimate. Sorry, the significance. If you believe it's supposed to be significant, but if they say the theory says that it is important variable to explain dependent variable, but when you estimate, you get insignificant. So there is possibility that the insignificant happens because of the multicollinearity. And then the signs of the estimate, okay, whether it is the sign similar to what we expect to see, based on the theory. If theory is just positive, then we get negative. So it's possible that that's the result of the multicollinearity problem. Number 5, so we have this just like before, assumption, income and wealth. The following cross-section model uses personal consumption expenditure as an independent variable. Annual income and wealth serve as independent variables. Perform appropriate test to see if there is multi-collinearity problem. So there are a number of things that you can do. First, what you can try to inspect is the correlation between variables. If high correlation, so there is you have to be aware. So meaning you have to be more careful because there is high possibility of having problems of multi-collinearity in the model. And then you can inspect the BIF, variation inflation factor. Okay, so you have data. Question number 5. So to inspect correction as I said before, so you can just one way you can just select the variables and then press Control. Income and wealth, and then you can just go to quick, as I said before, quick group statistic correlation in order to get the correlation between independent variables. Okay, and then you already put here the variable that we already selected earlier, and then just okay lah. Okay, so we get correlation between income and wealth 0.815748 or approximately 0.82. So the value is quite high, although not that high. Normally we have most of the time we have a problem when correlation 0.9 something, but this one 0.8 still high. So which is high enough to indicate that they could be multi-collinearity problem, but it's not an overwhelming evidence. And then if you inspect the BIF, variance inflation factor, you estimate whatever first. So meaning that you go to quick estimate equation. Okay, quick estimate equation. So we just estimate as usual consumption. And we have income. We have space wealth. Okay, so this one, just like before, the good practice is that before you estimate, you identify or you figure out the expected sign of the estimate. So just like before, we discussed before, income is supposed to be positively related to consumption, wealth also positively, and then after we estimate, we get both have the same, have the correct. So what we expect to have both now positive, just like what we expect for the two to have the sign of the two to have positive, and then p value for the individual testing, both are significant, both less than 0.05, which is consistent to the result of F-test. F-test statistic, which is we do not reject, we conclude that at least one, we reject. We conclude at least one of the parameter, the true parameter, to be not equal to 0. So consistent. And then you go to view coefficient diagnostic, BIF, variance inflation factors. So we get 2.98. so which is less than, not only less than 10, even less than 5. We mentioned just now, so that some will use 5 in order to say serious or unserious. Okay. For some researcher, but I think we just use 10. Even in the main textbook also use 10. So how to get the VIF 2.98? That is obtained by regressing income against wealth and get the R square and then calculate using the formula. You regress income against, so meaning that you estimate income space wealth, and then you get R square and you calculate, you get this one. You calculate using the formula 1 over 1 minus R square, you get this. Understand? Okay, I just quickly show lah. So let's say this one, how VIF is obtained. It is obtained through, if we regress one of the independent variable against other independent variable, wealth against income, wealth space C space wealth, income space C space wealth, and then okay, it's very different. So you get R square 0.665 or 0.67, and you calculate, you get 3.0 something, 3 point something. Yeah. So this indicates that multi-unity is only a small problem. Although correlation 0.8 is not too high, but can be considered as quite high. Okay, and then running a regression when income is dependent variable and wealth is the independent variable, or vice versa, meaning that you change wealth as independent variable against income as independent variable, and F statistic and A T statistic is a significant at 1% error level. So your R square 0.67, so you calculate the VIF, you get 3 point something. So again, this indicates that multiplicity is only a small problem, not that serious. It is supported by the estimate. So the estimate just now, the estimate of the model that has, the estimate that have correct sign as well as significant. Okay, so it means that there is no implication of serious implication of multi-equality problem. So we can just ignore the problem. So in theory, should income and wealth be correlated? Theoretically or logically, supposed to be lah. Because logically, those have better, higher income have better, better wealth. Income and wealth should be correlated to some extent, since both people who have higher income will eventually have more wealth. Then do your answer to part B and C agree with each other, or they are contradictory? So it might seem that the answers are contradictory, but they are not. It might seem that if you have income and wealth in the same model, there should be multi-causality, but in this particular data set, there is enough correlation between income and wealth that multiplicity is not a big problem. There must be some people in a data set who have high income but have not accumulated as much wealth as you might expect. Perhaps there are others in the data set who have lower income but have more wealth than you expect, that you would expect, because they are specificity or they inherited wealth from the parent, for example. Multi-causality is a characteristic displayed by the data. This means that for any model, one sample could give result that has big multi-causality, but a different sample might not. So it depends, different sample. So it just so again, that's why you can try to lessen the problem by adding more observation. So for this example, question number 5, we do not need to do anything. You just leave the problem. You just leave it. But the problem is not that serious as well. VIF, even VIF also, let's just 3 something. Question number 6. So this we have an example of 5 independent variables in the model. So our dependent variable is new passenger car sold. So sales of cars X1 CPI for new cars only, X2. Okay, so this one X1 we expect our prior expectation about the sign of relationship. We expect it to have we expect X1 to have positive influence on the sales of car because the price negative. So when price increase, we expect the sales to decrease. Yeah. So this one we expect to have negative influence on the dependent variable X1 and X2 also CPI also price as well. So X2 also we expect to have the same negative. X3 the personal disposable income. So when income increase, we expect sales to increase or decrease. Income increase, sales increase lah. So positive. X4 interest rate. So if interest rate increase, sales increase or decrease? Decrease. Interest rate increase, meaning that the cost of borrowing increase. So it discourages people to buy car. It is negative. The last one, employed, the number of labor force. The employed civilian labor force. So this one we expect to have positive influence. So more people work labor force, the larger size of labor force will increase the sales. We expect it to increase the sales. So it is positive. So this is our expected sign. So later when you estimate, compare and see whether it makes sense or not. If you get different sign, it is possible that that happens because of the multi-coordinality between independent variable. Again, because of the presence of coordinality between independent variables. So coordinality, negative, positive, negative, positive. So consider, let's say we decide to use double log model so that we can interpret a percentage, for example. So we use a double log model. So obtain the estimate and inspect. So is there multiplicity exists or appears or present in the model? How do you know? So estimate the model. This one. So use log model. Log log y space c, log x1, log x2, log x3, log x4, log x5. Okay. Now you inspect and see what we call as symptoms of multi-cardinality. So first, if you inspect the overall significant test, so it is significant, meaning that at least one to have significant influence. What we inspect the individual testing, only one X2 only to have significant. So the other variable, which is some of them also important, but it turns out that the result suggests it is insignificant. And then you inspect the sign of estimate. Just now, our prior expectation regarding the relationship between dependent and dependent variable, x1, we expect it to be negative. You get okay. So x1 we expect to be positive, to be negative, but here we get positive. X2 we expect negative, but we get negative. Okay lah. Okay, but x1 it is opposite to what we expect earlier. X2 okay. X3 we expect positive. Now we get positive. Okay lah. But it is not significant at 5%. Okay. And then X4 we expect negative, we get negative. Okay. X5 we expect positive, we get negative. So there are two lah, S1 and X5. X1, X5 to have different or incorrect sign of estimate, different from what we expect lah. So when we have different estimate as what we expect, then you have to investigate further to see if it is because of the cardinality between independent variables. So you read the given answers. Multi-cardinality may be present in data. First, R square value reasonably high, and F the significant overall test also insignificant. Only one T value is significant. Second, the general price index X2 has a negative sign, but the new car price index X1 has a positive sign. So the first one, the X1, may not make economic sense because the price increase normally is supposed to reduce the demand. But when the price increase here, you expect it produce positive estimate, which is quite not really make sense. So thirdly, neither the income variable X3 nor the employed variable X5 has any impact on demand because it's not significant, but rather surprise result. So X3 and X5. X3 is the income, X5 number of the size of labor force, and then the interest rate is also insignificant. So that is the symptoms of multi-cardinality problem. And then to confirm that, you can check the VIF lah. Okay, so you can further verify the problem by checking the VIF. So if there is cardinality, estimate the various auxiliary regression to find out which of the variables are highly linear. So after you estimate this one, if you regress log x1 against the rest, you get R square, you can calculate the VIF. You get VIF lah. And you regress log x2 against other x, log x1, x2, x3, x4, log x5, and then you get another R square, and you can calculate the VIF. You can do the same one by one. So this one you will get different. You will not get the same VIF because you have more than two variables. But in a view, you can easily get that VIF. You go to view, coefficient diagnostic, variance inflation factor, then you get VIF. So VIF here, as just now, this one, if we regress log x1 against the other 4 log x. This one, if we regress log x2 against the other 4 logs x. Okay, and so on. We get R square, calculate 1 over R minus R square. So you get this one. So you can see quite high. So when we regress each of these again other, so I mean we get quite large values even this one x2 x3 2000 something. Okay, so there is problems of serious problems of coordinarity. So in this case we need to do something otherwise our estimate to be not reliable. Our estimate as well as the result of Habermas testing not that reliable. So you have to do something to rectify the problem. So in this case we have to, if you are able to access more data, for example, try to increase some sample size. Increase sample size, you are able to get more data If you cannot, then the one way you can do to drop some of the variables, some of the independent variables. So now we need to decide so if there is severe correlativity, which variable will you drop and why? So now you have to make decision which one you should drop. One way to decide by looking at the cross correlation. So you inspect cross correlation table and see that can help us to decide which one is the most what we call that which one we should prioritize in excluding or removing that variable. So again, if you go to save time, I just copy this one. Copy this. You go to quick group statistic and for correlation. So you just type log x1. We want to inspect. So this one you have to inspect correlation between, because we are using log, you have to inspect correlation between log of x, not original value of x, but log of x1, log x2, log x3, log x4, log x5. So price of case you get this what we call as cross correlation matrix. Cross correlation matrix. So between x1 and x2, log x1, log x2, log x1 and x3, log x1 and x4, log x1 and log x5. So S given here in this table. So now we need to decide which variable you should exclude. So first you inspect the one that has high correlation. So you can we can see that we have high correlation between log x2 and x3 at the same time between log x3 and x5. So if you remove log x5, you still have the problem between x3 and x2. You see? So here we have the three quite high correlation. So there's one way So one of the way for us to, for example, how we can decide to drop which variable we should drop first in order to improve the estimate. So we have again a high correlation between x1, log x1, log x2, log x2 and log x3, log x3 and log x5. That mentioned just now, if you decide to remove x5 because it has high correlation between x5 and x3, but there is another problem, x2, x3 and x2. So instead of removing x5, you should remove x3, because if you remove x3, then we don't have this one, we don't have this one. Okay, so we don't have these two if we remove x3. So the x3 is the income. But we have another variable that also can as a proxy for income, level force as well. Level force, number of level force. And at the same time, x1 and x2 both are representing similar variables. So x1 and x2 both are CPI. The only thing is that X1 CPI for new car only, X2 CPI for all items. So basically X2 already cover the CPI for car. So because as X2 is CPI for everything, for all items, but X1 CPI index for car only, for new car only. So we should, these two are quite similar or related, so we can take out one of them lah. Okay, either X1 or X2. So in this case, let's say based on the table of correlation, we decide to take out X5 and any of X1 or X2. Okay, X5 because X5 have problem with X3. Sorry, we take out X3, not X5. Take out X3 because X3 has problem with X5 and X2. Okay, so we remove X3 and we also remove any of the X1 and X2 because both are the same CPI. I mean CPI representing the price, the price. So let's say we remove X2 and we remove X3 and then estimate model. So quick estimate equation, we have we remove X2 and X3. So we only retain without X1, X4, X5. Okay, so name as equation 2, equation 1, okay. So you get this one, and then you, if you again compare whether it is what similar to what we expect. So as one we expect negative, now negative, unlike before positive, but now negative. Okay, and then it is significant. Previously only one significant. The original model we only have one variable significant at 5%, but this one all three significant. All three significant, and then X1 now have correct signs lah. X5 before X5 negative, this expect positive. Now we expect positive, but now we get positive. Okay lah. Okay. Even if you inspect the VIF, it is still greater than 10. But in this case, in this problem, it doesn't seem to have this one greater than 19. It's not as large as before, but still greater than 10. But the estimate based on the estimate, it doesn't seem to have that problem lah. It doesn't have any implication on the estimate. So still significant, and correct sign as what we expect. So we can just use this result. Okay. Or alternatively, you can remove X1 and you keep X2 together with log X4 and log X5. Instead of X1, use log X2. So we get the same negative, positive, or significant. Even though we have some of them greater than 10, slightly greater than 10. So the alternative model is better than the earlier one. So compared to the original model, these two models have the correct sign for the various coefficient, and all the individual coefficient are significant. Okay. I thought we can finish earlier, already 9 or almost 9 as well. Alright, so yeah, we continue the next topic next week. Most likely next week we discuss not